what we're going to cover today is maxima and minima. Now, when we're talking about maxima and minima, we're talking about the highest place and the lowest place. Now, we can have what are called relative maxima and minima, which are taller than the closest thing around, or we can talk about absolute maxima and absolute minima. So, for example, if we want to talk about the absolute maxima on Earth, and we're talking about Mount Everest in Nepal, which is about 29,000 feet high, there's nothing on Earth that's taller than Mount Everest. However, we could talk about the tallest mountain in the United States, which is Mount McKinley, which is certainly taller than all of the other mountains in Alaska and in the continental United States. So it's taller than the ones near it, but it's not taller than Mount Everest. So we would call it a relative maximum. We could also talk about some of the mountains here in Colorado. They are relative maximums. They're higher than the places around them, but they're certainly not the absolute maximum. The absolute minimum on Earth depends on whether you're talking about on land or on water. If you're talking about on land, it would be the Dead Sea. The Dead Sea is about, what is it? I think I have it in here in my notes somewhere. At negative almost 1,400 feet, which is actually pretty remarkable when you think about it, the Dead Sea being that low. That's 1,400 feet below sea level. So that's pretty low. Now it is still water because, of course, water collects in super low spots, and it's a super low spot on Earth. But if you want to talk about just lowest spot on Earth and include the oceans, that would be the Mariana Trench. And the Mariana Trench is a negative almost 36,000 feet deep. So it is much deeper than Mount Everest is tall. You could take Mount Everest, plop it into the Mariana Trench, and it would not come close to poking up out of the water. It would still be short about 6,000 feet. But we can also talk about a relative minimum, which would be Death Valley in California, which is negative 282 feet. So this is the difference between an absolute and a relative. So absolute is just absolutely the tallest or shortest thing around, no matter where. Relative is, well, it's the shortest thing in this area. For us, that will be on an interval, say from 1 to 5. There are all kinds of problems where we're needing to look for the maximum and minimum. It could be maximizing profit, minimizing cost, minimizing the materials used in producing some kind of product, or finding the maximum height of something that's being projected. So there are all kinds of different ways of thinking about it. We're going to learn about what are called critical points. Critical points are places where the absolute extrema could occur, but they don't have to occur. So that they're critical points because they're places where those extremum values could show up. Now, when we say extrema, extrema is plural, extremum is singular. When we're talking about extrema, we're talking about a maximum or a minimum. So extrema and extremum include both the maximum and the minimum in one word. So these can show up only at critical points, but not all critical points are extremum values. So we're going to learn how they relate to one another. All right. Let's cover the definition for what an extrema value is. We have let f be a function. And the function has to be defined over the entire interval I, and let c be an element in I. In other words, c is one of the x values in this interval. We say that f has an absolute minimum on that interval at the value x equals c if the function value at c is greater than or equal to the function value for all x in the interval I. So what we're talking about is we have a number line here, and we have some interval, say from 1 up here to 5, and we've got some kind of curve, and it goes like this. And this point right here, c, that function value at c would, of course, be this value right here. This is the function value at C. And it is taller, higher than all the other f of x values near it. So we would say that f of C is a maximum over the interval 1 to 5. We say that it has an absolute minimum on I at C if f of C is less than or equal to f of x for all the x in the interval. Now, ours also has an absolute minimum, and it actually shows up at 2 places on I. It also shows up outside of I, but that's outside the interval. So we have 2 locations here and here. So we'll call this C1, we'll call this C2 and C3. So when we talk about the absolute maximum or absolute minimum, we're talking about the y value. So we're talking about f of C1, f of C2, f of C3. The minimum value is f of C2, which matches f of C3. That's the absolute minimum. The absolute minimum is the y value. Where it occurs, that's the x value. So make sure that you understand that the maximum and minimum is always referring to the function value at that point, the y value. Then if f has an absolute maximum on I at C or an absolute minimum on I at C, we say f has an absolute extremum on I at C. Extrema would be plural, extremum is singular. This is what's known as an existence theorem. So the existence theorem tells you that it exists, but it doesn't tell you how to go and find it. All right. So it's telling you what it is, but it's not telling you how to find it. It is possible if the interval is not closed or the function is not closed and bounded, that there is no absolute extrema in the interval. So what is a closed interval? A closed interval includes the endpoints of the x interval. All right. So when we're talking about the interval, we're talking about the where, not the what. The what is the y value. The where is the x value. So when we're talking about the interval, we're talking about the x value, and a closed interval includes the endpoints. We'll use square brackets to indicate that. Now, open intervals, in contrast, do not include the endpoints, and we use round parentheses to indicate that. So that would be like round parentheses 2 to 10, round parentheses. Now, infinity and negative infinity are a little bit tricky. Technically, they're considered to be both open and closed, which is kind of wild. How can it be both? It is a topic for real analysis, which is, of course, a junior level math major course, definitely beyond the level of our course right now. So you'll just have to accept that infinity and negative infinity are considered both open and closed. However, with infinity or negative infinity, we always use round parentheses, never square. What does bounded mean? When we talk about bounded, we mean that the y value is bounded by some other value. There's a finite y value that's either larger or smaller than all the y values over the interval. And the interval, of course, is consisting of the x values. Now, what does that do? Well, it eliminates intervals where the y value goes to infinity or negative infinity. Okay, so a bounded interval cannot contain a vertical asymptote. A bounded interval has to have all the y values below some certain point and above some certain y value. So they're contained, all right, trapped in between. And that excludes a vertical asymptote. Now, be careful here that you're sure that you understand that the term absolute is not referring to absolute value. It means nothing is taller or greater than that particular value, or nothing is smaller or lower than that particular value. All right. Now, the absolute extrema itself, if you have an absolute maximum, that does not guarantee it's positive. It could, in fact, be positive, negative, or zero. It's just the largest y value on that interval of x values. It could have an absolute max, an absolute min, or none. So let's take a look at some pictures and talk about what we've got in the pictures and what the different possibilities are. So the first one is the graph of x cubed on the interval from negative infinity to infinity. So this is not a bounded function. If we're looking at the entire thing, it is not bounded because the y values go to infinity and to negative infinity. If I restricted it to the interval from -2 to 2, the x interval from -2 to 2, it would be bounded because the y values would be between -8 and +8. So they're bounded by the value of 8 and -8 above and below. On the entire real number line, however, because it's not a bounded function, it has no absolute maximum and has no absolute minimum. Now let's look at the graph of 1 over x squared plus 1, again on the interval from negative infinity to infinity. Is this a bounded graph? It is a bounded graph. It is bounded above by the value of 1. There's no y value greater than 1. It's also bounded by 2, right? Or 3. It doesn't have any values greater than those. So we have lots of upper bounds, but we have a least upper bound, which is 1, because we do have a point where the y value is 1. So that's the lowest upper bound we have. Do we have a lower bound? In this case, we do have a lower bound. It's a little bit strange, but the graph approaches the x-axis both at the left side of the picture and at the right side of the picture. And as it approaches the x-axis, the values get smaller and smaller and approach 0. Now, does it ever hit 0? Well, no, it can't. Look at the form of the function. You have 1 divided by x squared plus 1. The only way to get 0 out of a fraction is to have 0 in the numerator, and you can't. You have a 1 in the numerator. So it's impossible for any of the values to take on the value of 0. 0 is still the greatest lower bound, all right? It is the lower bound that is closest to the function, but you can't pick anything larger than that because the function does get lower and lower and lower and approaching 0. So do we have an absolute maximum? We do have an absolute maximum of 1 at x equals 0. So the maximum is the y value of 1. Where it occurs is x equals 0. Do we have an absolute minimum? Actually, we don't. In this case, even though it's bounded below, it's going towards negative infinity and towards positive infinity. So we don't have a finite bounded x interval. And what we've got instead is it's approaching the axis, but it gets lower and lower and lower. So even if you say 1 over 1 million, I'll just say 1 over 1 billion, and that does occur. So there's no way to pick the lowest value. They're all approaching 0, but none of them actually get there. So it doesn't have an absolute minimum. Let's take a look at this graph, which is the graph of cosine of x over the interval from negative infinity to infinity. It has both an absolute maximum and an absolute minimum. Now, the absolute maximum is a single value, and it's the value of 1. It occurs at infinitely many places, right? So the absolute maximum is the value of the y value, which is 1, and it occurs at a lot of places. So it's occurring here at 0, and it's occurring over here at -2 pi, and it's occurring over here at 2 pi. And it will occur at every 2 pi multiples of those. So where it occurs is infinitely often, but the actual value that's the absolute maximum is a single value, which is 1. We also have an absolute minimum of -1, which occurs, of course, at multiples of pi over 2. So all the pi over 2 multiples of pi over 2, 3 pi over 2, etc., you have the value of -1. wait, not pi over 2, that's 0. Sorry, scratch that. The absolute minimum occurs at pi and negative pi and all the pi multiples of that, all right? So those are your absolute minimum values of -1, and it occurs in many, many, many places infinitely often, right? So we've seen a situation where there's no absolute max and no absolute min because it's an unbounded graph. We've seen a case where it is bounded, but we only had an absolute maximum and not an absolute minimum. And then we see another case where it is bounded. The interval is going from -infinity to infinity. And we have both an absolute maximum and an absolute minimum. Now let's take a look at some that are on more closed intervals, all right? Instead of from -infinity to infinity, let's take a look at these guys. This one is going from the closed interval from 0 to 4. So we're looking at this one right here on the closed interval from 0 to 4. This is I, our interval. Now, is it defined at all points? It is defined at all points. We have a jump here at 2. It's a piecewise defined function. F of x equals 2 minus x squared, f of x equals x minus 2. The first rule between 0 included up to 2 not included, x minus 3 between 2 included up to 4 included. Does it have an absolute maximum? It does have an absolute maximum. The y value of 2 is higher than all the other y values that get used on the interval from 0 to 4. It is a bounded function because it does have values that it never goes below and values that it never goes above. So it is bounded and it's on a closed interval. But the problem is we have a discontinuity here. And that discontinuity creates the possibility that we're missing one of our extrema values. And in fact, we have no absolute minimum. Now you may say, well, it should be -2. Well, it can't be -2 because -2 is not the value here at 2. The value at 2 is -1. That's a hole in the graph. It approaches the value of -2. But like the graph above that was approaching the x-axis, it never actually gets there. So you could say -1.9, and I would say -1.99. And then you could say -1.999, and I'd just go one more 9 after you. So there is no value that is lowest because they keep getting closer and closer to -2 without getting there, the idea of the limit. So this one has an absolute maximum, but no absolute minimum. Looking at the next one, it's defined over the closed interval from 1 to 4. So our interval here, I, is the interval from 1 to 4, right? So when we're looking at this one, notice that this is continuous over the interval. So it doesn't have this jump like this one did. And this jump caused a problem and basically eliminated the absolute minimum. This has both an absolute minimum and an absolute maximum. The maximum value is 4, and it occurs at x equals 4. It has a minimum value of 0, which occurs at x equals 2. So it has both an absolute maximum and an absolute minimum. So we're seeing that closed and bounded isn't quite enough. That closed, bounded, and continuous, however, might be enough, all right, to guarantee it. Now, this is one that we said is a problem because this has a vertical asymptote over the interval, and this is defined on 0 to 2. That means it's not a closed, entirely closed interval. When we go from 0 to 2, it's closed at 0, but open at 2. So it's not a completely closed interval, and it's not bounded because we have a vertical asymptote. The values are approaching infinity. There is no absolute maximum, but there is an absolute minimum. The lowest value is 0, which occurs at x equals 0. So as we're looking through these, we can see the different possibilities and what causes some to occur and not to occur. Breaks in continuity cause a problem, even if it is closed and bounded. So we're looking now to see what exactly the conditions are that would guarantee that we get an absolute maximum and an absolute minimum. And it turns out that closed and bounded plus continuity, that's the condition. Closed and bounded wasn't enough. We had some graphs that were closed and bounded. We're missing one or the other of our extrema or absolute minimums. In fact, I can give you a closed and bounded one that doesn't actually have either one, all right? It doesn't have a maximum or a minimum. So closed and bounded isn't enough. We've got to have closed, bounded, and continuous. Then that's enough. Okay. This is called the extreme value theorem. When we look at the extreme value theorem, we're talking about when those extrema values have to occur. When do we have to have an absolute maximum and an absolute minimum? If f is a continuous function over a closed and bounded interval from a to b using square brackets, then there is a point x between a and b at which f has an absolute maximum over the closed interval a to b, and there is another point x2 between a and b at which f has an absolute minimum over AB. So where it occurs is the x value. What it is, that's the y value. Now, the proof of this theorem is way beyond us at this point, but you just need to remember that you need both closed, bounded, and continuous, and then you will have extrema value. If the interval is open on one end or not bounded, then the function has at least one point of discontinuity, then it may not have an absolute maximum or minimum. It could have them, but it's not guaranteed. So now we want to take a look at what are the local extrema values. Local extrema values are related to what are called critical points. So critical points are places where these absolute extrema could occur, but not all critical points result in extrema. Some of them are, some of them are not. So local extrema and relative extrema mean the same thing. So when you see the two terms local extrema or relative extrema, these are synonyms for each other. Synonyms. All right, they mean the same thing as each other. They are not absolute extrema, they're just taller than everything around. So for example, Mount McKinley in Alaska is taller than all the other mountains in Alaska and taller than all the mountains in the United States. But it is not the tallest one on Earth, that's Mount Everest. Mount Everest is the absolute maximum on Earth, right? So when we're looking at these, we want to think about where we could get these maximums and minimums. So we want to look here at this graph, and we want to talk about what kinds of values produce these or how they're related to things. So when we look at this graph, I would pinpoint 3 places that I think have relative extrema or an absolute extrema. The absolute maximum to me is occurring right here at this corner type shape. So it looks to me like this one right here is an absolute maximum. It is higher than all the other y values on this entire graph. Now, what do we know about corners? They are what as far as being differentiable?
They cannot be differentiable.
They are not differentiable, right? So at a corner or a cusp, remember cusps look like this, that's a cusp. Those are not differentiable. So it looks to me like it is possible to have an extrema at a place where the first derivative does not exist, and it is. Places where the first derivative does not exist, but the function does exist, those are critical points. Those are one type of critical point. And the second part is important. I'm going to keep emphasizing that. The first derivative does not exist, but the function does. If the function doesn't exist there, you obviously can't have an extrema there. The function has to exist. So if you've got a corner or a cusp, it's possible that's a location of an extrema. The other two places that I think we should look at are this place right here and this place right here. Now, this is not an absolute maximum because this is higher. In fact, even these points are higher, but it is higher than the ones around it. So I would call this a relative or a local maximum. So you can call it either one. They tend to mean the same thing. I usually say relative because I think of it as being relative to the stuff around it, or you can call it local, meaning the same thing. So this is a relative max. This spot right here is not the lowest on the graph because both to the far left and the far right, the function is continuing down further, but it's lower than the points nearby, right? So if I look at this section here up to here, it's lower than everything else, and that makes that a relative minimum. What's special about those two places as far as the derivative goes?
It's equals 0.
Yeah, you're correct. That's a place where the derivative is equal to 0. So it looks to me like two places that I could definitely look to find an extremum value would be at a place where the derivative does not exist, but the function does exist, which would be a corner or a cusp. Or I could look for a relative maximum at a place where the first derivative is 0. Now, am I guaranteed that these are going to be places? No, I'm not guaranteed. And there is an exception in both cases, and I'll show you what they are. In the first case, there are actually 3 places where the first derivative does not exist. Corners is one, but that can be an absolute extremum. Cusps is one, but that can also be an absolute extremum. Points of vertical tangency. That's the third type. These do not result in points of absolute extrema. So right here at that one point, the graph of the tangent line went pure vertical, and the slope of a vertical line is undefined. And so that's a place where the first derivative does not exist. But these do not lead to extrema values. All right, so this is an exception. All right, the first derivative does not exist. The function does exist, but it's not going to give you a critical point. It's not going to lead to extrema. What about for places where the first derivative is 0, but it doesn't lead to an extrema? It's still a critical point, but it's not an extrema. This is a critical point, it's just not an extrema. This is the graph of x cubed. Right here at this one point, the tangent line goes horizontal and the slope of the tangent line is 0. So that at one point, one instant in time, it goes horizontal. However, looking at the graph, it's clear that that is not an absolute maximum and not an absolute minimum, nor is it a relative maximum or minimum. It's neither. This is what we call a saddle point. Now, I don't know how many of you like to hike, but saddle points are very frustrating when you're hiking in the mountains, because as you're hiking up the mountain, it looks like you're reaching the crest of the mountain until you come over the crest. And then you see that, no, this is just a flat part. And then the mountain continues to go up. So it comes up, flattens, and then goes up again. So a saddle point is a very disappointing thing when you're hiking because it means you're not done. You're not to the top yet. All right. So it's a place where it sort of makes a saddle on the mountain, and that's where they got their name. Right. So saddle points are critical points. The first derivative is 0. The function exists. The first derivative is 0, but it does not lead to an extrema. So all of these are critical points. Corners, cusps, vertical tangent lines, saddle points, and places where the first derivative is 0 and relate to hills and valleys. These are all critical points. But there are two that don't lead to extrema, and that would be the vertical tangent line and the saddle point. They're critical points, but they don't lead to extrema points. Okay. All right. Now we've already defined local maximum and local minimums, or absolute maximums and minimums. So now we'll define the local ones or relative ones and call it either one. A function f has a local maximum at x equals c. At is x value. If it says at, that's where. At x equals c, if there exists an open interval I containing c such that I is contained in the domain of f. What does that mean? Why did they say that? They just mean the function has to be defined on the interval. That's what they mean. The function has to be defined. If the function isn't defined there, how could it be a maximum on the function? So the function has to be defined. And if f of c is greater than or equal to f of x for all other x in that interval. That's it. It has a local minimum at a different x equals c if there exists some open interval I containing that x value c such that I is contained in the domain of f so that the function is defined there, and f of c is less than equal to f of x for all the other x in the interval I. Yeah, saddle point equals tantrum point. I love that. That's great, Lindsay. I've never heard that before, but that is so true. I can tell you that there have been times I come up over the hill and I'm like, you've got to be kidding me. I was looking forward to resting at the summit. Yeah, definitely tantrum point. Okay, a function f has a local extremum at c if f has a local maximum at c or if it has a local minimum at c. And remember, local is the same as relative. Now, what happens if we're talking about the endpoints? If we're talking about an open interval, we typically don't know what's happening outside the interval. If it happens on the interior of the interval, then we know we can establish that it will be a relative maximum or minimum or absolute. What if it happens near an endpoint if it's closed? The problem with having it happen at the endpoint of a closed interval is you don't know what's happening on the other side. To be a relative maximum, you've got to be larger than all the things on both sides of you. So saying that you think you have a relative maximum at 1 over the closed interval 1 to 5 is problematic because you don't know what's happening at 0. And 0 is to the left of that point at 1. So you really have to know what's happening on both the left side and the right side. So now we're going to look at some more graphs. We just want to go through and we want to determine where the local and absolute extrema are on each of the graphs. And we're going to assume that what we see is everything that there is on the graph, that there's not more existing outside of it. So looking at example 1, this spot right here looks like I have a relative max or minimum rather of -40 at x equal -3. The relative minimum value is the y value of -40 occurring at x equal -3. Now, if I look up here, it also looks like I've got a local maximum there. It's definitely not the absolute because the ones on the left go higher and the ones on the right go higher, but it's taller than all the ones between -3 up to almost 3. So it's taller than those. So when I'm looking at that, this means that I have a relative max, and it's hard to read this scale of this graph, is a little tight. I'm going to call it 10. Looks like relative max is 10 at x equal -1. Again, the extremum value is the y value where it occurs, X value. Now, this one is also a little deceptive. Stare really closely. If you have your notes open, stare really, really closely at what's happening here between 0 and 2. Do you see that there's this slight, well, it's hard to tell what's happening at 1, right? But at 0, it's higher. At 1, it's somewhere a little lower than it was at 0. And at 2, it's ever so slightly lower than that. Does everybody see that? Sometimes the extrema values are so subtle that if you don't know they're there, you won't be able to find them because you'd have to magnify it with a magnifying glass to see. Now, because this one seems to be decreasing over the entire interval, then I don't think that that's an extremum value. It does, however, look as though the tangent line would go horizontal at 1, but I think here at 1, we have a saddle point. It comes down, it flattens out, and then it goes down again. We have a false summit, a tantrum point, as Lindsay put it. I think we have a saddle point right here, but that is not an extremum value. All right, we would need to be able to magnify the picture to be absolutely sure, but it does look like it. Now, what else do we have? Well, the fact that it's decreasing from -1 ever so slowly until it gets to 2, and then it starts to increase again, tells me that right here at 2, I have a relative minimum. So I have a relative minimum, and it looks like it's 0 at x equals 2. Now, it could be slightly off of 0. So it could be something like, well, it looks like it could be slightly below. So maybe -0.99 or something like that. Really not 99. What would it be? -0.0001 or something like that. Really close to 0. All right. I'm not going to give you one where I expect you to be that accurate. Okay, so don't worry about that. Mine will be very obvious. Okay. And we're going to learn a better method today, of course, of finding them, which is going to have to use, as you know, calculus and algebra, because some of these are so subtle. If you don't know they're there, you're going to miss it. So there's got to be a better way of finding them, and there is. So we have a relative minimum here of -10 at -2. So what the relative minimum is the y value. Where it is the x value. Then it looks like I've got another relative max of -5 at x equal -1. It looks like there's a saddle point somewhere in here in this region around 0. There's a saddle point because it comes down, then it flattens out, and then it goes down again. So it looks like I've got a saddle point here. But saddle points, while they're critical values, because the first derivative is 0, they're not extrema values. But then it goes down, and I've got this little dip here at 1. So I've got a relative minimum here. And the relative minimum, eyeballing it, I'll call that 3 at x equal 1. As long as you're relatively close, that's good enough. And then I've got a relative maximum again, which looks like it's maybe at 7 at x equal 2. All right. But again, this is a terrible way of doing it, right? Because I'm really guessing. Do I know it's 7 and not 6.9? No, I don't. So it's a terrible way of doing it. All right, so there's got to be a better way. Let's identify the relative maxes and mins here. We'll just do these with balls. So I've got a relative maximum here, maybe 0.6 at x equal -2. I've got a relative minimum here of maybe -0.3 at x equal -1. I have a very definite saddle point here at the origin. This is a place that is a critical value. The derivative is 0. but it does not lead to an extrema because it keeps going up. It's a false summit tantrum point. All right, so then I have a relative maximum here, probably at 0.3 again. And it looks like these may be like mirror images, but reflected at x equal 1. And then it looks like this is also going to be a relative minimum of about negative 0.6 or 7 at x equal 2. Now on this one, if you ask me, I'm going to tell you that you have an absolute minimum, not relative, but absolute minimum of, oh boy, they're really testing me here. We'll make it negative 1.2. All right, and that is the absolute minimum. It occurs in two places. It occurs at x equal negative 2 and x equal 2, but I only have one absolute minimum value. The absolute minimum value is negative 1.2. It just occurs in two places. I have two relative maximum points, but I only have one relative maximum value. I have a relative max equal to about 0.3, and it occurs at x equal negative 1 and 1. So it occurs in two places, but really there's only one relative maximum value. Do I have a relative minimum? It looks like I do. It looks like I have a relative minimum here equal to, what would that be? I think that's about 0.5, I'm going to guess. It could be 0.1. Yeah, maybe it's 0.1. I meant 0.5, but let's call it 0.1 instead. But where does it occur? Well, it occurs over an interval. So it looks like it occurs at x between, say negative 0.2 to 0.2. So at all those values, it has that relative minimum value. But again, doing it from the graph means that I could miss something. There could be a very, very subtle bump up or bump down in what looks like a horizontal section that I miss because I'm not zoomed in close enough. So doing it graphically is a terrible way to do it. All right. So what we're going to use now are what are called critical points. Critical points are places where the absolute minimum or maximum could occur, but is not required to occur. We've already talked about the two types that we have. The critical point of f is where the first derivative is 0, or f prime of c is undefined, and I'm going to add a second part, and f of c is defined. The function has to be defined at that value. If it turns out it's a place where the function's not defined, then just toss it out completely. If the function doesn't exist there, it can't possibly be an extrema. All right, so what are we looking for? For the first derivative equal to 0, we're looking for hills, valleys, and saddle points. For the first derivative being undefined, but the function is defined, we're looking for corners, cusps, and vertical tangent lines. That's what we're looking for. All right. So those are the 6 different types of places where you can find critical points. Critical points are not guaranteed to be extrema, but if you have an extrema, it is at a critical point. This is called Fermat's theorem, named for Pierre Fermat. And he says, basically, if there is a local extrema at C, or absolute extrema, and f is differentiable at C, then it occurs at a critical point where the first derivative is 0. So basically what he's saying is if you have an extrema, it's got to be at a critical point. Not all critical points, though, are extrema. We saw saddle points and vertical tangency points are not extrema. So basically, we're looking for these things right here. This is a hill. First derivative is 0, but of course the function is defined. The second one is a cusp. First derivative is undefined, but f of c is. This is critical. This is the part many students forget to put on. And the third one is a corner. F prime of c is undefined, but f of c is. Because when you do these and you're looking for critical points, you are going to find places where the function's not defined. Those cannot be places where extrema occur, so you'll just toss them out completely. They are not actually critical points. Now we've got the other two here. This is a saddle point. First derivative is 0, but it's that false summit tantrum point. And then this is a point of vertical tangency. So the first derivative is undefined, but f of c is defined. And they've left off one, which is the minimum. And that's where f prime of c is equal to 0. I believe they left it off. Yeah, they did. All right, so that's another one. There are 6. 3 places where f prime of c is equal to 0. 3 places where f prime of c does not exist, but the function does. These are your critical points altogether. So I really need to add that one in here. I'm going to have to think about redoing these notes and adding that in. All right. So now we're going to go through and we're going to do these analytically, and we're going to look for places where the critical points could occur. Right. All right. So the first thing we're going to do is we're going to look for places where the first derivative either does not exist, but the function does, or places where the first derivative is 0. That means we need the first derivative. So now we're going to do the first derivative, which is 3x squared minus 24x minus 2, which is equal to f prime of x. All right. Now, looking at this one, we can tell that this is polynomial, which means it exists everywhere. So f prime of c always exists. So we don't have any where it's not. Right? Now, where's it equal to 0? Does this factor? What a terrible problem. No, it doesn't factor. So you would have to use the quadratic formula, which would give you the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. All right, so work that out. Give me just a moment. Okay, so 24 squared, I believe, is 576. Can somebody confirm that? This is 12 plus 24 over 6. So I'm getting 4 plus or minus the square root of 600 over 6. So I've got 4 plus or minus. Now we've got 100 times 6, so that's 10 square roots of 6 over 6. So that gives me 4 plus or minus 5/3 square root of 6. All right. Now, what we want to know is, are those the critical points? Yes, they are the critical points. Now, what we're going to do is we're actually going to graph this and see if these are places that end up being critical values. So I'm kind of stretching it a little tight there. Let me see if I can make it less tight. Or maybe I can find it off my notes. That would be a little easier. There it is. Okay, so I'll type it in here. Y equals x to the third minus 12x squared minus 2x plus 1. Okay. Now, we've got 2 points right here. This one is, it's hard to say, but it looks like it's at about negative 0.82. I want someone in class to find me the approximate decimal values of 4 plus 5/3 square root of 6 and 4 minus 5/3 square root of 6. What do you have when you get those two values? What approximate values do you get? Somebody?
8.020824, sorry.
Like
No,
that?
no. Without the 0.2 in the beginning. Yeah, like that, sorry. And then just 0.0824.
0.0824, something like that.
Yeah, that's what I got.
Okay. Do we have any agreement from the rest of you?
I got negative 0.0824.
And it should be negative. Why? Look at the picture right here. What do you have here in your graph? What have we got? Let me shorten up the scale, or expand the scale rather. Let's go down to 200. And let's go up to okay, that's a little better. What have you got right here? I'm trying to find the maximum. Where is it? It's giving me the maximum right here of 0.082, 1.083. It's a critical point and it's a relative maximum. What do you suppose this value is right here? 8.082. It's a relative minimum and it corresponds to the other critical point that we got. So will they always be extrema values? No, it could have been a saddle point, all right? These came from the first derivative equal to 0. So they're either going to be hilltops or valleys, extremum, or they're going to be saddle points, which are not, all right? Let's take a look at the next one, which is a little bit easier to graph. We've got 4x cubed minus 3x. We have to find the first derivative no matter what to see where it's undefined and to see where it's 0. So we're going to find the first derivative by getting 12x squared minus 3. And this is always defined. What are you looking for to say it's not defined? In general, what is the one situation in math you must never, ever do?
The denominator, so like
you cannot divide by Thou shalt
Zero.
not.
0.
0. Thou shalt not divide by 0. So typically, the one type where you're looking for corners and cusps comes from the first derivative has division by 0 at a single point or a couple of points. That's typically what you're looking for the first derivative to be undefined, but you have to make sure that the function is defined at that point. Make sure it's not a hole in the graph, which would eliminate it from being an extrema. So now we have f prime of z, when is f prime of x equal to 0? So we set 12x squared minus 3 equal to 0. I can divide by 3. So I get 4x squared minus 1 equals 0. I can solve for x squared, and that gives me x squared equals 1/4. And when I take the square root of both sides, I have to put in a plus or minus, and I get 1/2. So I've got two possible critical values. Am I guaranteed these are extrema? No. But if it has an extrema, it has to be at one of these 2 points. There's no other place it could occur. So now we'll take a look at this graph, which was 4x cubed minus 3x. All right, so we've got our graph right here. It looks like we have a relative maximum here at bingo, -0.5, and a relative minimum here at bingo again, 0.5. So we know we found the correct critical values, and in fact, they are relative extrema locations. The actual extrema are 1 and -1, the y values. Where they occur are the critical points. Right? Now let's look at one with more difficult function. This is the natural log of x minus 2. Now you have to be careful with natural log because natural log is only defined where the argument is strictly greater than 0. So we're going to start here with the domain, which is x minus 2 has to be greater than 0. It cannot equal 0. Natural log of 0 is not defined. So it's only defined for the argument greater than 0. So this means x has to be greater than 2. So we're looking at the interval from 2 to infinity. So if we get a critical value of 2, we can throw it out. It's not in the domain. All right? It's not in the domain. So now we want to find the critical values. So we take the first derivative, which is 1 over u times the derivative of u, which is x minus 2, that's chain rule, which gives me 1 over x minus 2. The derivative of x minus 2 is just 1. So I get 1 over x minus 2. This is never equal to 0. Again, the only way to get a fraction equal to 0 is to have the numerator equal 0, and we can't, so we'll toss that out. But if the denominator is equal to 0, it's undefined, and that's when x equals 2. But f does not exist at 2. What does that tell you about the graph?
Can be a jump.
It's not a jump. It's defined. There just are no critical points. There are no critical points. Think about what the graph of this must look like. It's been shifted over to 2. So we have a vertical asymptote at 2, and it goes like this. There's no relative maximum. There's no absolute maximum. There's no relative minimum. There's no absolute minimum. It goes up like an arm, increasing like this, like the typical natural log shape. There's just no extrema. There's no critical points, so there's no extrema. It doesn't have a hill or a valley. It doesn't have a corner or a cusp, right? So it just looks like that. There are no critical points, so there are no extrema. let's look at the next one, which is tangent of x. We have tangent of x is equal to the y value. So let's take the derivative. F prime of x is equal to the derivative of tangent is secant squared of x. So now we have two things we have to think about. Type number one, f prime of, well, let me put x. F prime of x equals 0, or type 2, f prime of x does not exist, DNE, but f of x does exist. All right, so I'm asking you, where is secant squared of x equal to 0? Secant squared of x, when does it equal 0? Who remembers the graph of secant? Do you remember how you take the graph of cosine and you kind of turn it inside out? So the graph of secant squared is going to be a little different, but remember, the graph of secant never touched 0, right? In fact, it was from 1 to infinity and from -1 down to negative infinity. It never came close to 0, ever. So if you take values that are never close to 0 and you square them, do you think we're going to get 0? Let's try it. Let's take this out and let's look at the graph. Is that ever 0? No, it's never 0. Secant squared can never be 0. Another way of thinking about it is this is 1 over the cosine of x squared. Can you make that equal to 0? Obviously, you can't now, because you can see that the numerator is a 1. And since the numerator is a 1, it's impossible to make it 0. So there are no critical points coming from the first type. So there are none. On the other hand, over here, we've got f prime of x does not exist. When does secant squared not exist? When cosine of x is 0. So when is cosine of x 0? These are at the pi over 2 multiples of pi over 2. So whenever x is equal to pi over 2, 3 pi over 2, or the negatives of all of these, etc., then it's not existing. But does secant exist at those points? We know the derivative doesn't exist there. Does secant exist there? Well, let's look at the original graph. The original graph is tangent of x. So now we've got to put tangent of x on here and decide if it exists at those values. And what we want to see are multiples of pi over 2. So we'll change our step here into pi divided by 2. Uh-oh. What do you see in the graph of the original function tangent of x at all of the multiples of pi over 2? I see vertical tangent lines, right? Or vertical asymptotes, rather. Okay, they are vertical tangent lines, but they're vertical asymptotes. In fact, tangent is not defined at pi over 2 because it's sine over cosine. So if cosine is 0, it's not defined. So I have none from that either. Right? None. F of x also does not exist. So I have no critical values. So what it's telling me is on the graph of tangent of x, and I'm going to take the first one off, on the graph of tangent, I have no extrema. This is like the graph of natural log. There's no extrema here. There's no hill. There's no valley. There's no corner. There's no cusp. There's no place that's taller than any of the others because it goes towards infinity, and no place where it's lower than the others because it goes towards negative infinity. The graph of tangent of x doesn't have any extrema. So the graph reinforces what I found analytically, which was that there were no critical points. Right? Now, example 6 are some that I really like to do. These are ones where we have x to the 3 halves or x to the 5 halves. I like to give these because these produce some really interesting graphs. They're more interesting than some of the plain old polynomials, which get kind of boring after a while. So these are kind of fun to do. So we're going to look at this and we're going to find the critical values by finding the first derivative using the power rule. So remember to bring the 3 halves to the front, subtract 1, which is 2 halves. So that will give you x to the 1 half minus 5 halves brought to the front times the 3 that was already there. X to the 5 halves minus 2 halves is 3 halves. Now we can clean it up a little bit. We can say this is 3 halves x to the 1 half minus 15 halves, or 7.5, writing and talking, x to the 3 halves. All right. Now, it may help you on this one to think about the domain. The domain of this one is affected by the x to the 1 half and x to the 3 halves. X to the 1 half is actually the square root of x, and x to the 3 halves is going to be the square root of x cubed. Or you could write it as the square root of x cubed. Put the cube inside the square root. I tend to do the cubing after. All right, which means that our domain here is going to be affected by that, which means that we can't put a negative underneath there, right? So we can put 0, but not a negative, right? So when we're looking at these, we're looking to see what is going to be the critical points. We have 2 types, f prime of x equal to 0. That's the first type. And then the second type is f prime of x does not exist, but f of x does exist. Now, we have not seen one of these yet, all right? We have not seen one where the first derivative didn't exist, but the function did. We've seen a couple where the derivative didn't exist, but the function didn't exist either. So that's different. We haven't seen a type 2 yet. So first off, we need to take this 3 halves x to the 1 half minus 15 halves x to the 3 halves, and we need to set it equal to 0. So we have 3 halves x to the 1 half minus 15 halves x to the 3 halves. Now this is going to be some tricky algebra, and this may be something that you have not actually ever done before. So it may be something that's really new to you. And if it is, then you'll learn how to do it today, and then you'll be able to do it from now on. Okay. All right, so looking at this one right here, the first thing I'm going to do is I'm going to factor out the 3 halves. 3 halves is a common factor of 3 halves and 15 halves. And I'm also going to take out the x to the 1 half. What does that leave behind? Remember that factoring is actually a form of division, all right? So when you think of it, think of what do I have to multiply this by to get back the original. So 3 halves out of 3 halves leaves behind a 1. X to the 1 half taken out leaves behind the 1. So I have 1 there. And then what would I have to multiply 3 halves by to get 15 halves? I'd multiply by 5. And what would I have to multiply x to the 1 half by to get x to the 3 halves? When the bases are the same, add the powers. So I'm thinking here about x to the 1 half times x to the something equals x to the 1 half plus the something, which equals x to the 3 halves. That's the process you're going to. When the bases are the same, you add the powers. So to add to 1 half to get 3 halves, I would have 2 halves. And x to the 2 halves would have to be equal to x So this becomes 1 minus 5x. And this is set equal to 0. Now the question is, when does this not exist? Well, there's not a problem with the polynomial part. This exists at all times. What about when this does not exist? Well, it only doesn't exist if the value of x is negative, but looking at the original, the domain doesn't include those values anyway. So that's not going to be a type 2. So when we're looking at this, we have two possibilities. We have 3 halves times, and we might as well write it the square root of x equal to 0, or we have 1 minus 5x equal to 0. So this first one basically says the square root of x is 0, which means x is 0, or 1 equals 5x, which means x equals 1/5. So we have two possible critical points, or we have two critical points from the first one. We have 0 and we have 1/5. All right. Okay, what about part 2? Part 2 is f prime does not exist, but f does exist. Well, I don't have any of those. The only place where the derivative does not exist is when the values are negative. But the original also has that problem because the original has x to the 3 halves and x to the 5 halves. So I have the square root of x up there as well. So I don't have any coming from there. So none. So let's take a look at what this one looks like. X to the 3 halves minus 3x to the 5 halves. Let's see if I can remember that long. Is that it? All right. Now, this one is decreasing and it looks like it decreases forever. We'd have to do some more calculus on it to be sure. We can take the first derivative and see if it's positive or negative. If the first derivative is negative, it's definitely decreasing forever on that interval. But do you see how it's got this small blip up here? So let's scroll in, scroll to make it more obvious. Aha! It looks to me like we do have a maximum value at 0.2, which is, of course, 1/5. So we have a relative maximum at that, but it was hard to see. It was really tiny. But we knew to go look at that point because analytically, we had already solved for critical points at 0 and at 1/5. Now, is 0 a relative minimum? There's nothing to the left side of it. So you could only say it's a relative minimum from the right side. All right. In general, we typically say that it's only a relative minimum or maximum if it's on an interval. And since we don't have the interval to the left side, we would generally say it's not a relative minimum. We would only say the one at 1/5 is a relative maximum. Okay, let's take a look at this one. This is with division. How many of you would rather do it as a quotient rule, and how many of you would rather do it as a product rule? You can put it in the chat or give me a thumbs up. Shuri is voting for the product rule. I know Caleb prefers the product rule. How about the rest of you? Okay, well, we'll go with Shuri's. Remember that all quotient rules can be turned into the product rule if you want to. All you have to do is take the factor that's in the denominator and raise it to the -1 power. And that makes it into a product rule problem instead. Okay, so you can always avoid the product rule. Michael agrees, he wants the product rule. Okay, so we'll do the product rule. I don't know what it is about the quotient rule, but it just really messes things up. Okay, so looking at this one, we need to find f prime. So remember our formula, we have a little f and a little g. These are different f's and g's from the original function. So we do f prime g plus g prime f. So the derivative of the first factor is going to be 2x multiplied by the second factor, which is, I don't know what happened right there. Oh, that's my g there. It was too close to the 2. It looked a little funny. So I have x squared plus 2x minus 3 to the negative 1 plus g prime. Now we have to do chain rule. So we have a negative 1, freeze the inside, don't change it, then times the reduce the power by 1. That's power rule. So negative 1 to the front, freeze the inside, reduce the power by 1, and now multiply by the derivative of the inside, which is going to be 2x plus 2. Right? So that's f of g, f prime of g of x times g prime of x. Right? And then we multiply this by the first factor, which is x squared minus 1. So all this part right here is the derivative of the second factor raised to the negative 1 power using the chain rule. Now we can clean it up a little bit and we can drop what's raised to a negative power to the denominator again. So we have 2x over x squared plus 2x minus 3 raised to the first power plus a negative, and then this is going to be dropped to the denominator, x squared plus 2x minus 3. It'll have to stay in parentheses because it's being squared. And then we have 2x plus 2 and x squared minus 1. Now, it would be easier to put a minus in between instead of plus a negative. So now we have the minus. Now, the question that we have now is, what are we going to do to get it in one combined form? We want one combined form so we can decide when it equals 0 and when it's undefined. So having it as one fraction makes that easier. So what we're going to do is we're going to multiply the first fraction by the factor x squared plus 2x minus 3 and the numerator by the same. So we're multiplying by a form of 1. So we're not changing the equation. We're just changing the way it looks. So our first derivative then myself a little more space is going to be, and I'm going to distribute this out. So I've got that times that, that times that, that times that. So I end up with 2x cubed plus 4x squared. You guys check my algebra here, minus 6x. Everybody okay with that? So far, so good? Minus, and I'm going to put the second part in parentheses because I can only do so many things at one time before I start making sign errors. So I'm going to multiply these two out using FOIL. So I get x squared times 2x, which is 2x cubed, 2 times x squared, which is plus 2x squared. 2x times negative 1 is a negative 2x. And then 2 times negative 1 is a negative 2. Now I left a little bit of extra space, so I'm going to write directly above it what it would be if I incorporated the negative signs. So this would be negative 2x cubed minus 2x squared plus 2x plus 2. And then all of this is divided by the common denominator, x squared plus 2x minus 3 squared. I never said it would be easy to do this analytically. I just said it's better than doing it graphically. Okay, so let's combine like terms. We've got a 2x cubed minus 2x cubed, so that cancels out. Then I've got 4x squared minus 2x squared, so that gives me a 2x squared. So I've taken care of that one and that one. And then I have a minus 6x plus 2x, so that's a minus 4x. So I've taken care of that one and that one. And then I have my plus 2, all divided by x squared plus 2x minus 3 quantity squared. And this is my derivative in the single combined form. The next thing I need to do then is I need to take these and I need to look for where the first derivative is 0 and look for where the first derivative is not defined, but the function is. So I have two types. Type 1, f prime equals 0. Type 2, f prime does not exist, but f does exist. Looking for my coffee. Now, f prime equals 0, that's going to come from the numerator equal to 0. So equal to 0 is going to be referring to the numerator. So I'm going to take my 2x squared minus 4x plus 2 and set it equal to 0. The only way to have a fraction equal 0 is if the numerator equals 0. Then I'm going to divide every term by 2 to get rid of the common factor. And then I have x squared minus 2x plus 1 equals 0. And does that factor? I believe it does factor. I think this is x minus 1, x minus 1. Doesn't that work?
Yeah,
That's
that's what
okay.
it is.
All right, so I've got x equal 1 as a possibility. All right, so I have x equal 1. Going back to the original, however, thinking about the domain, what do you notice up here in the original, in this original denominator, x squared plus 2x minus 3?
When it equals 1, it's 0, so it's not defined.
It's not defined. The function is not defined at 1. If I were to factor the original so I could find the domain, whoa, what happened? Okay, x plus 1, x minus 1 over, this would be x minus 1, x plus 3. What happens to the x minus 1s in the original function? They cancel, right? And that creates a hole. I have a hole at x equal 1. So even though I got it as a critical value of type 1, the function doesn't exist there because it's a hole. So I have none from this part. I thought I did, but when I check the domain, I don't. Now, what about the type 2s? The derivative does not exist, but the function does. When I'm looking for where the derivative doesn't exist, I'm focused on the denominator. So I want the denominator not equal to 0, but the function does. So when I look at this one, I need to factor the denominator. So I've got where denominator is equal to 0, but function exists. Now remember, I looked at the original and I found that the domain up here is going to be all reals except 1 and -3. So if I get 1 or -3, the function doesn't exist there. I'll have to throw those out. And of course, guess what you're going to get? So we're going to look where the denominator is equal to 0. So x squared plus 2x minus 3, quantity squared equals 0. Take the square root of both sides. So x squared plus 2x minus 3 equals 0. And it factors x plus 3, x minus 1. And we get 2 possible critical points. But f doesn't exist at either. So there are none. So we have no critical points. So if we were to graph this, what you're going to find on the graph is that it doesn't have any relative extrema, it doesn't have any absolute extrema. So let's take a look at what it looks like. Scroll back to my normal. What was it? X squared plus 2x minus 3. Did I get that right?
Yep.
Okay. Now let's look at the graph of it right here. Do you see how it doesn't have any relative minima or relative maxima? Yes, this curves down, but notice this keeps going down, 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 down. In fact, it's approaching a horizontal asymptote of 1 as it goes off towards negative infinity, but it never gets to -1. So there is no relative minimum there. And on the right side, there's no relative maximum because although it approaches again the horizontal asymptote of 1, it never gets there. It gets higher and higher and higher and higher, but it always stays below 1. And so there is no relative maximum either, and there's no absolute min or max. Okay. Now we want to talk about locating the absolute extrema. Now remember, the extreme value theorem said that if you have a closed, bounded interval and it's continuous, all three, closed, bounded, continuous, then it has to have an absolute maximum and an absolute minimum. Where could you find it? It could be at one of the endpoints, all right, of the closed interval, since they're included, or if it's on the interior, then it needs to be at a critical point. So when you're looking at a closed bounded region, you can find an absolute extrema at the endpoints or at a critical point. So now we're going to take a look at some of those. All right. Problem solving strategy for finding absolute extrema on a closed bounded interval is first evaluate the function at the endpoint so that you know what it is at the endpoints. Then find all the critical points of the function that occur inside the interval between the open interval from A to B. Then find the function value at those critical points. Then compare the function values at the endpoints to the function values at the critical points. Pick the highest one for the absolute maximum. Pick the lowest one for the absolute minimum. But again, three conditions: closed, bounded, continuous. And continuous is not a minor condition. It's a major, major condition. Remember, it means the function exists, the two-sided limit exists, and they're equal. Okay, so now we want to look at this one. We want to find the absolute maximum and absolute minimum of this function over the closed bounded interval 1 to 4. So we're going to look at 1 and 4. So endpoints are the first place we check. So endpoints, f of 1 is equal to 1 squared minus 4 times 1 plus 3, which is, what is that? I got 0. Is that what you guys got?
Yep.
Okay. All right. So everybody agrees on that. All right. so now we want to take a look at the next part, which is at 4. So 4 squared minus 4 times 4 plus 3, which is going to be 16 minus 16 plus 3. I got 3. Everybody agree on that? Okay, so I have 2 candidates. My candidate so far is 0 for the absolute extremum and what else? 0 for the absolute extremum and 3 for the absolute maximum. All right, so that's not enough. Now we need to check the critical points in the interval open 1 to open 4. So I have to find the first derivative of the function, which is going to be 2x minus 4. There are 2 possible kinds. F prime of x equals 0, but f exists. And 2, f prime does not exist, but f exists. All right. Now, when I take the derivative, 2x minus 4 is a polynomial, so it definitely exists everywhere. So that's not a problem. Now, what I want to do is I want to take a look at the next part, which is going to be setting it equal to 0 and solving. So 2x minus 4 equals 0 means 2x equals 4 or x equals 2. So I have one critical value. The original problem was a polynomial, so its domain is all reals, so it's definitely defined at 2. So now I need to find the function value at 2. So I'm going to take my next step, which is critical points. I only have one. There are none here since the first derivative always exists. So f of 2 is going to be equal to 2 squared minus 4 times 2 plus 3. That was my function, right? Yeah. So that gives me 4 minus 8, which is a negative 4, plus 3 is negative 1. All right. So I need to compare the values negative 1, 0, and 3. Which one is the smallest between those 3? Which one is the smallest value?
Negative 1.
Negative 1. So negative 1 becomes my absolute minimum. Of negative 1 at x equal 2. And my absolute maximum of 3 at x equal 4. Okay, I'm going to now work example 9, which is to find the absolute maximum and absolute minimum of the function sine x cosine x over the interval from 0 to 2 pi. So it is a closed interval. The domain for sine is all reals. Domain for cosine is all reals. So there's no place where the function is not defined. So we know that the domain is defined for all reals. So there should be no place where it does not exist. So now what we want to do is we want to find the first derivative, and we also need to evaluate it at the endpoints. So this time I'm going to find the first derivative first, and then I will find the function value at the endpoints and the critical point last. So f prime of x, we're going to have to invoke product rule. So we're going to have sine x times cosine x. Sine x is the first factor, cosine x is the second. So derivative of sine is cosine times the second factor cosine of x plus the derivative of the second factor cosine is negative sine x times the first factor, which is sine x. This is going to give us cosine squared of x minus sine squared of x. Now, this is also a double angle formula. And if you happen to remember that it's a double angle formula, it will make your life a lot easier. This is the cosine of 2x. So we're looking for two situations where either the first derivative is 0 or the first derivative does not exist. So our first one is f prime equals 0, but f exists. And that's going to be where the cosine of 2x is equal to 0. Now, we know that cosine is going to equal 0 whenever we have multiples of pi over 2. All right, so multiples of pi over 2. So going back to your trigonometry, we have 2x equal to pi over 2 plus k pi. All right. Now we only need to check over the interval from 0 to 2 pi. So we only need to go over that interval. So basically, we have two possibilities in there, but we're going to keep it pi over 2 plus k pi until we can get all of them figured out. So we have 2x equal to, we'll get a common denominator. So we have pi plus 2k pi, all divided by 2. And once we have a common denominator, we'll divide by 2. And when we divide by 2, we end up with x equals pi plus 2k pi over 4. Now we'll go through our list, and we're going to create a list using k values equal to 0, 1, 2, 3, and -1, -2, -3. And then we're going to find the ones that fit in the interval from 0 to 2 pi. So our k value is going to start with 0, then 1, then 2. We'll see how far we need to go. And then -1, -2. When k is 0, I just get pi over 4, which definitely fits within that interval. So that's definitely one that's a possibility. All right. That's one of the ones I'll have to check. Then when k equals 1, I add another 2 onto the 1. So that gives me 3 pi over 4. So that gives me another one in the interval from 0 to 2 pi. And then I would add another 2 pi over 4 onto it, and that would give me 5 pi over 4. And that's definitely still in the interval. So I need to keep going until I find one that falls outside 0 to 2 pi. So the next one that I'm going to do is going to be 7 pi over 4, which is approaching the end of 2 pi, since 2 pi is 8 pi over 4. But I can test it by going to the fourth one. That's 9 pi over 4. And this is outside my interval. So this is outside 0 to 2 pi. So I ignore it. Not that it doesn't give me a 0 value for the cosine of 2x. It's just outside the range of the interval I'm looking at. Then I can try a -1. That would be pi minus 2 pi over 4, which would be a negative pi over 4. And so that one would also be outside the range. So I would mark that one out because it's outside of my interval from 0 to 2 pi. So I have these possibilities right here: pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are all critical values. Those are the ones where the first derivative is 0, but the function exists. Now, my derivative is cosine of 2x. So the second thing I need to check is f prime does not exist, but the function does exist. Do I have any of those? And the answer is no, because cosine of 2x has a domain of all reals. So it exists for all values. So there are none coming from the second type. Right? Since there are none coming from the second type, then I'm ready to go ahead and evaluate at my critical points and at my endpoints. So I need to find the function value of the original function, f of x equals sine x cosine of 2x, or cosine x. All right. So let's rewrite the original function so we remember what it is. Sine x cosine x, and our interval is 0 to 2 pi. So I need to evaluate the function at the endpoints first. So that's going to give me f of 0, which is sine of 0 times cosine of 0. Now sine of 0 goes to 0, cosine of 0 is 1, but this still gives me 0. Notice that the f of 2 pi is going to give me the same result since those are the same place on the unit circle. So I get sine of 2 pi times cosine of 2 pi, which is still going to give me a 0. Now I need to evaluate it at my 4 different critical values. So my 4 different critical values are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So when I'm looking at those, the first thing I can do, if I can get my Word to stop saving, it's saving and saving slowly. It's the bar that never closes. Okay, so f of pi over 4 is sine of pi over 4, cosine of pi over 4. Now, sine of pi over 4 is 1 over the square root of 2, and cosine of pi over 4 is also 1 over the square root of 2, so I get 1/2. So that's a greater value, so it's now my candidate for the absolute maximum. Now I'm going to test 3 pi or 5 pi, no, 3 pi over 4, that's next. 3 pi over 4, and then 5 pi over 4, and then 7 pi over 4. So let's test f of 3 pi over 4. So that's going to give me sine of 3 pi over 4. So now I'm over into quadrant 2. So if you're wondering where we are, we've gone 1, 2, 3. So we're over here. This is 3 pi over 4. We're in quadrant 2, but it's still a reference angle of 45 degrees. So the values are still magnitude 1 over square root of 2. We just have to worry about the signs of them. So remember, in quadrant 2, sine is positive, so I get 1 over the square root of 2, but cosine is negative, so I get times a negative 1 over the square root of 2, which gives me a negative 1/2, which is smaller than both 0 and 1/2, so it's now my candidate for the absolute minimum. And then I'm going to have f of 5 pi over 4, which is going to put me down here into quadrant 3, where both sine and cosine are negative. So when I multiply sine of 5 pi over 4 by cosine of 5 pi over 4, I have a negative 1 over the square root of 2 times another negative 1 over the square root of 2. So I get 1/2 again. So since this ties for the value at pi over 4, my candidate for absolute maximum is still 1/2. It just occurs at 2 places. And then I'm going to evaluate f of 7 pi over 4, my last critical point. And this is going to put me into quadrant 4. And in quadrant 4, we know that the cosine is positive, but the sine is negative. So now we're over here in quadrant 4, and we end up with negative 1 over the square root of 2 times 1 over the square root of 2, which is a negative 1/2, all right? So again, what we've got down here is we've got all of these different values, and this is another place where we get a negative 1/2. So 0 is not any of them. So it is not an absolute maximum. It's not an absolute minimum. It could be a relative, but it's not max or min. And in fact, because they're at the endpoints, it's not even a relative, because a relative has to occur at an interior point. So now we have 1/2 and negative 1/2 as our extrema values. So we have an absolute maximum of 1/2 at x equal pi over 4 and 5 pi over 4. So it occurs at 2 places, but the maximum value is singular. It is 1/2. And the absolute minimum is equal to -1/2, and it also occurs at 2 places, at x equal 3 pi over 4 and at 7 pi over 4. So the absolute minimum is again a singular value, -1/2, occurring in 2 places, right? And if we want to, we can take a look at the graph between 0 and 2 pi. So coming over here to Desmos, we can graph y equals sine x cosine x. I think it will do that correctly, but only graph it from 0 less than equal to x less than equal to 2 pi. If I can find my I. Y equals, and it didn't like that. What did it not like? Let's maybe put that in parentheses. There we go. It wanted to know for sure what the factors were. So I had to put one of them in parentheses. Now here's my picture. It's only graphed over the interval we're interested in. And we see that we do have, in fact, a couple of relative extrema, which are the relative max at pi over 4 and 5 pi over 4, and the relative minima at 3 pi over 4 and 7 pi over 4. But the relative extrema values are 0.5 and -0.5. Okay? And we can add that to our pictures. Let's take a look at one with an exponential. These are always kind of challenging problems. And I think they're interesting because they sometimes lead to some strange critical points and some strange behavior. So we have xe to the -x/2 as our function. The exponential has a domain of all reals naturally, and there's nothing in the power -x/2 that would eliminate any x value. So the domain of e to the -x/2 is all reals. The domain of x is all reals. So the domain of their product is all reals. So the domain here is going to be all reals. So the function exists at all points. We're interested in the interval from 0 to 5. Okay, so the first thing we're going to do is we're going to find the critical points by finding f prime, and f prime equal to 0, and then f prime not existing, but f existing, and f exists everywhere. So f prime invokes the product rule because we can think of this as x times e to the -x divided by 2, where the -x/2 is all in the power. Then e to the -x/2 is going to invoke the exponential rule, not the chain rule. Well, it will invoke chain rule, but not the power rule. All right, so the derivative is going to be the derivative of x, which is 1, times the exponential unchanged, plus, now we take the derivative of the exponential, which is e to the u, times the derivative of u. And the derivative of -x/2 is a -1/2. And then we multiply by the first factor, which is x. So cleaning this up, we have e to the -x/2 minus 1/2 x e to the -x/2. Now, typically, when you do something with an exponential, you want to factor the exponential out of the expression. So when you factor the exponential out, you get e to the -x/2 times 1 minus 1/2 x. Now, why do you want to factor out that exponential? The reason is very simple. Exponentials, by their nature, either look like this, where they're increasing functions, or they look like this, where they're decreasing functions. In either case, what do you know about them? They never touch the x-axis. They never are equal to 0. So when we're looking for places where the first derivative equals 0, it's never going to come from an exponential function. So we can eliminate that from the first part. So we're looking for first derivative equal to 0, but f exists. So that we know that the exponential is never equal to 0. And the second one, we can set up 1 minus 1/2 x equals 0. So that means 1 equals 1/2 x. And when we solve it, we get x equal 2. I'm creating a little space here. All right. So we have x equal 2 as one possibility for a critical value. Now, what about the first derivative not existing? So come back up here to the first derivative and look at it. Exponentials exist everywhere unless there's a problem in the power. So you can ignore that. There's no problem with negative x over 2. It exists for all x's. So the exponential does. And 1 minus 1/2 x is polynomial, so it always exists. So part 2, saying that the first derivative does not exist, but f does exist, is not going to happen because it always exists. So we have none coming from the second part. All right, so what do we do now? Now we want to compare the function value at the endpoints 0 and 5 with the function value at the critical point, which is 2. So we're going to take our values and we're going to look at the endpoints, and the endpoints were 0 and 5, and our function value was x e to the negative x divided by 2 in the power, and our interval was 0 to 5. And our critical point was 2. All right, so we have all the information down that we need to find. So we need to evaluate f at 0, which is going to be 0 times e to the 0 divided by 2 with a negative on it. E to the 0 is 1, so this gives us 0 times 1, which is still 0. F of 5 gives us 5 times e to the negative 5 divided by 2. Now we're going to have to take a calculator and get an approximate value for that, because really I have no idea what that is. It is some positive value because e raised to a power has got to be positive. So 5 e to the, I can't see in here too well, e to the negative 5 halves. I got about 0.4104. So it's not a great deal larger than 0, but so far it's my candidate for the highest value. So the next thing that I want to take a look at is the value at the critical point, which is f of 2, which is going to be 2 times e to the negative 2 over 2, which reduces to 2 times e to the negative 1, which of course is 2 over e. And this is approximately equal to, I can multiply that out, times e to the negative 1. And that's about 0.7358. So that is higher. So then we can say that we have an absolute maximum of 0.7358, or I'd more likely use the true value, which is 2 divided by e. So we have an absolute maximum of 2 over e at x equal 2, which was our critical point. And we have an absolute minimum. This minimum value is 0, which is lower than 0.4. And that occurred at x equal to 0, right? And if we take a look at our graph, then we can hopefully see that. And we're only on the interval from 2 to 5. So we're going to look at that. And our function is x e to the negative x divided by 2. Did it enter that correctly? Looks like it did. Okay, so you can look at the graph right here. You may have to scroll in a little bit to see that it really does have a maximum value. All right, and our maximum value, of course, is right there at 2. And the minimum over the closed interval is right here at 0. We have 0 at 0. Okay. So we have 2 more to look at. One of them is x natural log of x over 5. This is example 11. So we want to think about, first off, what's the domain? When will this function exist? When does it not exist? Remember that x by itself, the factor x at the front, is polynomial. So it exists everywhere for all values of x. But natural log, the second factor, only exists when the argument is greater than 0. So on this particular one, for the domain, we need to have x over 5 greater than 0, which basically means that x is greater than 0. So our domain is going to be open 0 to infinity, right? So any critical value we get that's 0 or negative is not going to work because the function's not defined there. So now we're going to take a look at the derivative. So we get f prime, we're going to invoke the product rule. So this is x times natural log of x over 5. And the natural log part will invoke chain rule. So we get the derivative of x, which is 1, times natural log of x over 5 unchanged, plus the derivative of natural log is 1 over u du dx. So 1 over u is going to be 1 over x over 5 times the derivative of x over 5, which is a 1/5, and then times the first factor, which is x. Remember that the bottom of the bottoms flips to the top. So this becomes the natural log of x over 5 for the first term, plus 5 over x times x over 5. Now, notice that we get a lot of cancellation here. So a lot of things are going away, and we basically end up with the natural log of x over 5 plus 1, right? We still have a placeholder. Now, the next thing we want to do is we want to find the critical points. So we have 2 options. We have f prime equals 0, but f exists. So it's got to be greater than 0. Or we have the second one, f prime does not exist, but f does exist. So again, it's got to be greater than 0. All right. So looking at our particular derivative, which is natural log of x over 5 plus a 1, where the 1 is not in the argument, we could turn it around and write it as 1 plus natural log of x over 5, which probably is better, because then you don't make the mistake of thinking the 1 is part of the natural log. So this is probably a better way of thinking of it. So we'll box that up right there. Okay, so if I'm looking at this right here, when is that equal to 0? Well, when is that equal to 0? When is natural log going to be equal to 0? Well, natural log equals 0. Let's see. So we need to have 1 plus the natural log of x over 5 equal to 0. Now, I know that the only way to get it to equal to 0 is to have the natural log of x over 5 turn out to be -1. So this happens when the natural log of x divided by 5 is equal to -1. So if I have the natural log of x divided by 5 equal to -1, oops, my thing is going crazy on me again. I can solve this by switching to exponential form. So if I switch to exponential form, then my base is e, the power is -1, and it equals x divided by 5. So my base is e, I can get this to stop saving, maybe it'll come back to me. And the bar that will never close. There it goes. E to the negative 1 equals x over 5. So when does x, what does x equal? So this happens when x is equal to 5e to the negative 1, which is the same as 5 divided by e. So that will happen whenever it's 5 divided by e. Okay, so that's going to be my critical value there when x is 5 over e. And 5 over e, I don't know what it is, but it's about, well, e is about 2.7. So it's around 2. It's a little less than 2, but something like that. Now I want to look at where the first derivative does not exist, but the function does. The first derivative, the one always exists, polynomial. Natural log doesn't exist only when the argument is 0 or less than 0. But that's the same condition for the function to exist. So I don't have any cases where the derivative doesn't exist, but the function does. So there are none of these. I do have cases where the derivative doesn't exist, but it's the same places where the domain doesn't exist either. And that would be both 0 and below. So I can ignore that. All right. So I really only have basically x natural log of x over 5 as my function. So my function is x natural log of x over 5. And my interval that I was looking at is 0.1 to 5. Notice it doesn't include 0. That's not allowed. So 0.1 to 5. So I need to evaluate the function at all of these points. So f of 0.1 equals 0.1 times the natural log of 0.1 divided by 5, which is approximately equal to natural log of 0.1 divided by 5 times 0.1, which gives me, we'll call it negative 0.3912. And then the function value at 5 is equal to 5 times the natural log of 5 over 5, but 5 over 5 becomes 1, and the natural log of 1 is 0, so this equals 0. So I have a candidate for absolute minimum, and I have a candidate for absolute maximum. Now I need to evaluate it at the critical point, which is 5 over e. So now I have f of 5 divided by e, which is a little less than 2, which is going to be 5 divided by e, natural log of 5 divided by e divided by 5. Or another way of looking at it, and maybe a better way of writing it, is 5 over e times 1 over 5. Notice that the 5s will cancel, and we get the natural log of e to the negative 1, which of course is going to give us a negative 1. All right. So then this will give us a 5 over e natural log of e to the negative 1, which is 5 over e times negative 1, which is negative 5 over e. And negative 5 over e is approximately negative 1.8394. So that then becomes the absolute minimum value, and our absolute maximum value is going to be 0. So our absolute maximum is equal to 0 at x equal 5, and our absolute minimum is going to equal, that looks like a C, is going to equal negative 5 over e at x equal 5 over e, which was the critical value. And again, we can graph this one so we see what it looks like. So we have x, natural log of x over 5. So 0.1 to 5, x, and then this should be natural log of x. Did I do an x there? I did not. I did a c. X divided by 5, I believe. Oops, wrong place. All right, so now we've got our values here. So we've got a minimum value here, which is our 1.839, and the minimum value is the y value, negative 1.839, which is what we got, negative 839 at 1.8394. Let me see if I can get it back on the right spot. And then our maximum value is 0 at x equal 5. All right, we have one left to do. We're going to do a nicer one, a more fun one compared to the harder ones we've been doing. This is just a polynomial. And because it's a polynomial, the domain is going to be all reals. So the function exists at all points. So now we're looking for the absolute maximum and the absolute minimum. Remember, I said that infinity and negative infinity are considered to be both closed and open. So I can consider it to be closed and open. Now, I'm looking for an absolute maximum and an absolute minimum, but I may not have one because of the negative infinity to infinity. It could go to negative infinity forever. So we're going to look at this graph. I'm going to start with the derivative. So f prime of x is equal to 12x cubed plus 24x squared minus 36x. All right. Now that's the derivative. The derivative is defined everywhere because the derivative is also polynomial. So there will be no type 2's. So type 2 is f prime does not exist, but f does. But there are none of these because the first derivative is polynomial and always exists. So then we look at the type 1's, which is f prime equal to 0. So we take 12x cubed plus 24x squared minus 36x and set it equal to 0. The first thing I'm going to do is divide by 12 to reduce the numbers, but I am not going to divide by x. If I divide by x, I lose a critical value. You never want to divide by the variable. When you divide by the variable, you lose critical values. So what I'm looking at here then is I've got x cubed plus 2x squared minus 3x equals 0. I leave the variables where they are. Now I want to factor it. So when I factor it, first thing I'm going to do is take out the greatest common factor, which is x. And that leaves behind x squared plus 2x minus 3, which is a trinomial that factors. And it factors into x plus 3 times x minus 1. We saw this earlier in the set of exercises. So we have 3 critical points. Our critical points coming from the first type are x equals 0, x equal negative 3, and x equal 1, those 3 points. Now we want to evaluate. I can't evaluate at the endpoints because infinity and negative infinity are not numbers. So we're going to have to be very careful on this one. We don't have that, so we're going to have to look at the graph to be absolutely sure we've got it right. So the next thing we have is 3x to the 4th plus 8x cubed minus 18x squared. So f of x is equal to 3x to the 4th plus 8x cubed minus 18x squared. So we're going to evaluate at each one. F of 0 is 0. F of negative 3 plugging in -3 and evaluating it at each point, you're eventually, you can check, but you're eventually going to end up with -135. And then f of 1 is going to give you 3 times 1 to the 4th plus 8 times 1 cubed minus 18 times 1 squared, which gives you -7. There is no absolute maximum. All right? Why is there no absolute maximum? It's a 4th degree polynomial, which means the ends go up forever. They go to infinity, so there can't be an absolute maximum, but there can be an absolute minimum. The reason that this one fails to have an absolute max is because it's not bounded. It's closed, it's continuous, but it's not bounded. So you've got to have all 3 to have that. So now what we've got is, instead, we're going to have an absolute minimum of -135 at x equal -3. Well, then what's this -7? It's probably a relative minimum. So we probably have a relative minimum there. In order to know for sure, you'd need to look at the graph. So when we come over here, we'd take off our condition for the interval, and we would simply enter the rest of the function, which the function was 12, what was it? No, 3x to the 4th, 3x to the 4th plus 8x cubed minus 18x squared. All right. So when we're looking at this one, you can see that we do have a relative maximum here, but it's not an absolute maximum. And then you can see coming down here that we have a relative minimum of -7 at 1. But we've also got more of the graph over here. So if I move this aside, see how it has to go up on both ends. I've got to have something way down there. So if I come in here and I change my range here to be maybe down to -200, something like that. I don't think that did it. Oh, it didn't change. And we'll make this go up to 10. And scroll in a little bit. I don't know if we can find it. It's going to be way, way down here. It's apparently not taking my values. Aha, there it is, right there. And that gives us the -135 at -3. This is the end of this particular video, and in the next one, we'll be discussing the mean value theorem.